welcome to Last Minute Maths again. In this video, we're going to do a very quick revision of graph transformations, all right? And when we move curves around or stretch them, reflect them, etc. And just run through that as quickly as possible for some of my students. And if you have any questions, as always, please do put it in the comments or if you want any clarification. Right. So what are graph transformations? Well, if you start with any graph, all right, and where its function is f of x, right? So that could be, for example, y equals x squared, or x cubed, or y equals a straight line, for example, 5x minus 2, etc., whatever it might be, okay? Starting with that basis, if we then change the function or the graph itself by, let's say, the first one here, so f of x plus a, all right? So that could be, if we started with x squared, so that could be, for example, x squared plus 2, yeah, a particular number. And it can be plus or minus, all right? So it could be x squared minus 3, for example. So if we have a positive number, then that's going to move the graph, the whole graph, move it up, all right, by a units. So in this case, it'll be 2 units. Everything will just go up by 2, all right? If it's a negative number, then it'll move down, obviously. And for this particular example, for example, the whole graph moves down by 3 units. So if I try and illustrate that with some sort of simple little diagram, then imagine we have, this is our original f of x, so that's our original graph, all right? And we can then move the whole thing, okay? Let's see, how do we do this? Okay, so that's gone up by 2. So that effectively is f of x plus 2, all right? That's what it would look like. Everything literally just goes up. So you can do this with coordinates as well. If we say that that coordinate is 3 minus 1, the new one, the x coordinate does not change, all right? But the minus 1, it goes up by 2, so it'll be 1, 3, 1, all right? And if we were to move it down, it would have the same effect again. So let's see, just something like, etc. All right? Not too artistic today, but we'll make it work. So this one would be f of x, let's say, minus 1. All right? So the new line, right, comes down to 3 and minus 2. Okay? So that's basically how the graph will move. The shape does not change. Stays same. Okay, nothing else changes, just the whole thing moves. Only y values change. All right, okay. The second type that I'm going to cover is the reflection type. All right, so when you have a minus in front of the function, so minus f of x, that reflects the whole graph in the x-axis, all right? So it just goes upside down for simple language, all right? And if you have the minus sign inside the brackets, then that is a reflection in the y-axis. So then you're just going side to side. So flip, yeah, but undo that. All right, so you're flipping it side to side. So in this case, I'll illustrate that again. And, oh, let's see if I can do this right. Like that, for example. Again, not the best artwork, but let's be patient with that. So this is going to be f minus f of x, all right? So that basically flips it upside down. And remember, this was your original f of x, all right? And if you're flipping it side to side, okay, then it's going to be exactly the same thing on the other side and the right way up, okay? So let's go there, shall we? And something like that, all right? Oops, yep, that's fine. So this one is f of minus x, all right? So this one flips it to the other side of the y-axis, and the minus f of x flips it upside down. So just about the x-axis, if you like, all right? Okay, the third element we're going to look at are the movements left and right. So if you have a movement like the plus or minus a inside the brackets, like here, all right, then the graph will move sideways. So inside bracket, a constant, right, equals sideways, all right? And that applies in every case, really. Now, this one's a little counterintuitive, a little opposite to what you might expect. When you have x plus a inside the bracket, so f of x plus a, you actually move it to the left, all right, by a units. And when you have a minus a, so f of x minus a, your original graph will move to the right, okay? Because of the plus and the minus, positive or negative x-axis, you might think of it the other way around, but please make a note of this, all right? And again, to illustrate, if I were to move this, let's see, that would go this way, for example, okay? So that's f of x minus a, and I could have it going this way. Oh, that's terrible. Let's do that again. Let's put it here. Okay, and that would be f of x plus some number a, all right? Again, if you had an x coordinate here, for example, this is 2 minus 1, then you could move it, this could be, for example, 5 minus 1 for that minimum point there. That's where it goes to. So that effectively could be f of x minus 3, all right? It moves it 3 units to the right, okay? And the other way around, we've got 1, 2, 3, 4, 5. So that could be f of x plus 5, okay? This point here, the minimum point, that's going to become minus 3 minus 1. All right. It's very typical in GCSE exam questions to give a graph without even doing a diagram, but to give you like an equation of a graph or just f of x, give a transformation and ask where a new coordinate will be. So they'll give you a particular point, for example here, and they'll ask you where the point will be moved to. And that's when you need to play with the x or y coordinates, all right? And in this one, only x coordinate changes, all right? And just to retrace the thing here, in this one, in the reflections, all right, in the minus f of x, that one, y coordinate change of sign. So you reverse sign of y coordinate only. And for this one here, you reverse sign the x coordinate only. All right, I hope that makes sense. I should have mentioned that earlier. Right, and just to finish off the last couple of bits, this last bit is actually probably the most difficult to visualize. All right, let's give it a go. If you have a factor multiplying the function, okay, so a times f of x, not plus minus, but timesing, okay, then that becomes a stretch vertically. If it's on the outside of the f of x, i.e. a times f of x, then you stretch vertically by a scale factor of a, right? So scale factor. And what that's going to do, let's say I have, I'm going to change it to f of x, and I'll put a 2 in front of it, right? 2f of x. Taking the graph that I've got here, my standard f of x, what's going to happen is that all the y values are going to double. So here, that one, it's just going to go up to here, right? So whatever value it was, it's twice as tall now. Same here, that one doubles. This one, again, let's say it's -1, right? So that's what, 3, put that in, 3 minus 1. I don't want to mess with the thing just yet, but I'll show you in a moment. That one's going to go down to here, so it's going to become -2, all right? And, oh God, this is going to be difficult to draw, but I'll try. The zero values don't change, all right? They will stay the same. So I'm going to try and hit those points. Not the best graph in the world, but as I said, you get the picture, all right? So these ones have been doubled, times 2, times 2, not plus 2, times 2. And again, the -1. So if it was 3 minus 1 at the minimum point, now it becomes 3 minus 2, all right? So the y coordinate is multiplied by the scale factor. All right, the x remains same. X value stays the same. All right. Okay, hopefully that makes sense. Just excuse the poor artwork. The last one, the one that I think catches everybody out at some point or another, is what happens when you have the factor multiplying inside the bracket. So f of ax, all right? So this one is actually a stretch horizontally, as you might guess, but this is the trick. The scale factor actually becomes 1 over whatever the multiplier is. Okay, so if that is a, the scale factor is 1 over a. So imagine if we had 2x, all right, that actually multiplies the whole graph by half, all right? The x values are multiplied by half. If you had a quarter times x, it would actually multiply the graph x values by 4. So that actually becomes a stretch, all right, proper stretch. And the 2x becomes a compression, if you like. That's a stretch. Means it gets wider if it's a fractional multiplier, and this one is actually a compression. All right, just move that. So you're squeezing it, and it's going to become narrower. Okay, so let's illustrate that. Okay, so let's take what example can I take? In this particular case, I'm starting with a point that's 4 and -1. all right? If I were to apply the 2x to it, all right, then all the x values get multiplied effectively by half, all right, or they move to what their half position would have been. So let's try and illustrate that the best I can. That's going to go here, and it's going to be narrower, remember. Okay, so this is effectively that, all right? What that means is when x equals, for example, 6, all right, it takes on the value that it would have had it been 12, all right? That's not to confuse you, but those of you who like the detail, that's effectively what you're doing. But just remember the whole thing. You times all the x values by half, basically, which is counterintuitive, which is why I'm spending more time on this. And if I were going to, let's say, have that quarter, all right, maybe I'm not going to stretch it that far. Let's call it times 2. And then that will go way over here, all right, and be much, much wider. How do I do this now? I'm going to use a different color, let's say. So that one will be like this, all right? So that will be f of half x, right? Which is the same as f of x by 2, okay? That's the more tricky one to visualize, and I hope the scale is just about right. Yeah, I think that's okay. So this one, as I said earlier, is counterintuitive, and you've got to watch out for that one. That's the main one that causes people a problem, right? So basically, you don't multiply the x's by a, right? You do the reverse. Times all x values by 1 over a. That's the important thing, all right? And y values stay same, okay? Now, if we take a particular example, one that I was doing with one of my students earlier on, all right, they gave, so I don't know, example here. They gave a particular graph. It said there is such a curve, y equals f of x, all right? And they say it's transformed to y equals f of minus x minus 3, all right? And then it says there's a point, I think it was like p equals 7, 2, all right? And that moves to a point q, which has obviously xy coordinates, and they want the coordinates of q itself, all right? So let's examine what's going on there. You've got, all right, that's the transformed function, all right? So use this separately. The first thing to do is always do the inside brackets part first, all right? So this is reflect sideways, right? So in y-axis. And if you remember what we said earlier, that means the x values change the sign of the x values, all right? So that is going to turn that value, the 7, 2, that we started with, the first transformation is going to do that. It's going to become minus 7, 2, okay? Then the second part, remember, is a move, and it's a minus 3, so it's going to move down by 3, all right? And that's going to affect only the y coordinate. So the y coordinate will be reduced by 3, okay? So the last part is this, so minus 7, and 2 minus 3 is going to become minus 1, All right, so that is the position of Q. So they're the coordinates of Q. So they are treated independently, the transformations. Always do the ones inside the bracket first, and then whatever goes on outside of the brackets, i.e. outside of the f of x. And that should hopefully keep things in the right order for you. Right, if there's any questions, please do drop it in the comments. And if you found this useful, please do consider subscribing and liking, sharing, and all those wonderful things. Right, good luck with your revision. Thanks for watching.